Hi, there is a common feature between these three instruments. So the first one on the left we have already seen. So this is altitude digitizer. As you can see, there are 9 outputs, A1 to C2 here. This is an encoding altimeter. We will test this thing in a future video. So this has an output also, a parallel output in order to have a quantification of the altitude. And this big guy on the right is an air data computer. So this is a vintage electromechanical air data computer from the 70s. So this is 590 D1 from Collins. And as you can see, there is also a digitizer incorporated in this instrument. So you have 10 bits here. So the common point between these three instruments is the digitizing altitude. So this is used for the transponder. The resolution is 100 feet. So the altitude is sent to the ground station and also to other airplanes in order to avoid the collision. So this is used by the TCAS system. In order to test this feature, I have designed an indicator in order to display the altitude. So this will be the topic of this video today. At the end of this video, we will test this digitizer here. So we have already tested, but only with LEDs. So then we can test the accuracy of this thing. So let's see now this indicator I have designed. Several years ago, I have designed a small indicator for a nuclear power plant application. So this is this indicator here. As I have several prototype boards, I have modified one in order to realize this altitude indicator. So this is the original schematic. So there is a OLED display here, 2 lines of 16 characters, a small peak processor here, 24F family. So there are the few input-outputs. There is also a Sigma Delta ADC here with the 3 differential inputs. I have modified the schematics, so I have removed the DC-DC converter and I have added this circuit, which is 2 shift registers in cascade. And there is here on the left the 11 inputs. So there is a pull-up, which one input connected to plus 5 volt. And these 11 signals are the input of the shift registers, and the command lines of the shift registers are connected to the microcontroller here. So this is a modified board. So this is the OLED display. And this is the small daughter board with the 2 shift registers here. And this is a DC-DC converter in order to provide the 5 volt DC from the input voltage, which is 28 volts. Okay, and this is connected to the microcontroller directly. So the outputs of the digitizer are open collector or dry contact. For example, this instrument has open collector outputs. You can see my video if you want to see some details about this thing. I will place a link on the screen or on the comment. But sometimes it can be also dry contacts. Like the air data computer. I bought the manual of the Collins air data computer, and this is the encoder inside this instrument. So this is a metallic drum, which permits to have an electrical contact. There are some insulators here in order to avoid the contact. So this thing is linked to a gear in order to have the complete altitude range in one turn. So I'm going to reinstall everything, and then we can make some tests on this device. So there is a LEMO connector for the power supply here. So the power supply is set to 28 volts. I am going to turn on the power supply. Okay, so it shows invalid code because there is nothing connected. So the configuration bit 000 etc. is invalid. So I have built also this test feature here. Permits to set one of these 11 bits one by one. So we can use also this cable. It will be easier for testing. Okay, so this is the 00 configuration. So there are 3 different modes in this instrument, which are available using these push buttons. So the first mode is the display of the altitude in feet. The second one is the display of the altitude in meters. And the third one is for debugging. I have the state of all these bits. So we can see that we can set any of these bits, and so this permits to know if there is a missing bit or something like that. So you return to the altitude mode. So this is a specific code which is called Guillaume code. I don't know if I pronounce correctly. So it is a kind of gray code, that is to say that there is only one bit change between two adjacent altitudes. So this permits to avoid the wrong measurements when there is a change of altitude. The Guillaume code is described in a US patent. So this is this patent here. So we can see that the original patent has a maximum. So the maximum altitude with this 10 bits. So these are 10 bits here. Unfortunately, D4 is not available, and you have to place the jumper. So we can test, for example, this configuration, 18,200 feet. So 0, so the D4 is here. Okay, so 1, 1, 0, 1, 0, 1, 1, 0, 0, and we have 18,200 feet. Okay. So I have used an algorithm in order to translate the Guillaume code into a binary code. So I have tested first the algorithm using Excel sheet. So you will see now a small video I have done when I have tested this algorithm using Excel. This is an Excel sheet I have wrote in order to validate the algorithm. So I have used some Excel functions in order to calculate the result. So the functions I have used are the bit shift on the right here, and the exclusive OR, and also the modulo function, which is the remainder of a division. So the input data is here. There are 11 bits. LSB is here, C4, and the MSB is D2. On this line, there is an equivalent value of this data in decimal. So you can see the configuration of this data correspond to one of this altitude. I don't remember which one, but for example, we can check the first line here, which is the altitude 18,300 feet. So 0, 0, 1. 0, 0, 1, 0, 1, 1. So you can see that this thing works. We can check also another one, this round value, for example, 20,000 feet. Every bit is at high level except C4, C1, and D4. take C4, C1. Okay, C4, C1. Okay. You can check also another one. For example, the last one here, 28,800 feet. So every bit is at O level except C4, C4, B2, A1. Okay, so this works. So we'll implement this function in C language into the microcontroller, and after that it will be possible to test some encoding altimeters. So I have connected the indicator to the altitude digitizer here. So the input of the digitizer is connected to the air pressure generator here, and the pressure is monitored by this manometer here. So we can see that for null pressure we have an altitude of minus 100 feet. What we can do is to set different air pressures and compare to the result of this table we have already used several times, and compare the altitudes. So for example, I will set an altitude of 10,000 feet. So I will increase the pressure, I mean in the negative side, that is to say a pressure below the ambient pressure. Okay, I will decrease. Okay, so we have 10,000 feet, and we can see that the pressure is minus 322 millibars. So the absolute pressure is 1013 millibars minus this pressure. So I will do the calculation. Okay, so this gives a pressure of 691 millibars. And if we look at this table, we can see that we have 697 millibars. It is not exactly the pressure, but maybe the ambient pressure is not exactly 1013 millibars. So we can test another one, for example, 20,000 feet. Okay, so we have a pressure of minus 553. So we'll do the same calculation, 1013 minus 553. Okay, so this gives an absolute pressure of 460 millibars. And we can see on this table that the absolute pressure should be 565 millibars. So we are very close to this pressure. Okay, we can test the GIAM code also. Okay, so you can see that between each adjacent altitude there is only 1 bit change. Okay. So this was the test of this indicator. It seems working perfectly. So it is possible now to test the output of the air data computers or altimeters, which has an encoding altitude. So in the next video, we will see the air data computer from Collins. We will start with the altitude section. As I have the documentation, it will be easy to make working this thing. Thank you for watching. See you next time. Bye.